I want to talk about graph generating functions. And by that I mean we have a function which takes in a vertex. It might also be the vertex and the graph. It might be some sort of local graph around the vertex. But in this case it would just be like a vertex, which is a special case of that. Then we return sort of a list of edges that we want to add to the graph, how it currently is. And in this case, we want to construct this graph over here, and we start from the blue vertex, and then we just basically say, if this blue vertex has no edges, which is this case, then we add 2 new vertices. If the vertex has already one edge, we add 1 vertex to the vertex. Makes sense?
I think your types are wrong.
No? Why are they wrong?
It's not a vertex, it's like a vertex set.
No. It's just single vertex. I assume though we can look up what the edges are of the vertex. In this case, we only need to know how many edges does this vertex have. This is the only feature this function here uses, and then this graph is generated. Generated if this is a function which is sort of called, we start with one vertex. Let's say now we call the function, does something. Okay, call it again on the resulting graph, but not again on this vertex over here, which already we called it on. It just on each vertex that was generated in the last step. And we do that forever. That generates line graph.
They gotta make it out. I'm a black Scottish cyclops. They got...
You understand this function?
I think it's wrong. There's no recursion, right?
Yeah, that's like not in this function. It's just like we use this function and we call it on every vertex that we have. And we do that iteratively for each new vertex that was generated in the last step.
And why is there 2 times 0?
And this is, ignore this other thing here below. So it's not part of this function.
And what's vertex dot unique? I mean, I guess I understand the intuition, but
give me a new unique in this index. If we assume a vertex just like natural number, that means just give me a new natural number that wasn't used before. Or generate a UUID or something. Just some unique identifier, basically.
Okay.
So we want to have functions like this that generate a graph, because this graph is infinite, right? I can have an infinite line graph, and I won't want to store an infinite graph, so I can store this function instead, and this procedure that constructs this graph using this function. Whereas this procedure of just call this function for every vertex, that's always the same, that's constant. The thing that is like that sort of describes that this line graph is this function. And we want to be able to analyze, well, the idea is we have the world state graph, and we want to infer the graph generating function for the world state graph, or for regions of it, because that captures the structure of the world. Makes sense?
So the generating function is like a particular world model.
That's how you could think of it, yes.
Okay.
Insofar as the world state graph is the world model, the generating function generates that world model, because it generates that graph.
Okay.
Okay, let's see, what would be the next best thing to talk about?
Yeah, maybe tell me, if you have more advances, you can tell me more about that.
Well, so here's the thing. This notation I was using before is kind of cumbersome, and it's kind of... So my intuition is that maybe it is actually extremely easy to write an algorithm that just generally detects the structure, for any kind of structure we could have, because intuitively, what the algorithm just needs to do is it needs to be like, if I'm starting with this vertex, what kind of operation? It's like we have some graph. Okay, let's say we have, well, okay, let's do the line graph example again. So you could be like, yes, I'm like observing that I have this kind of graph, sort of like infinite line graph. This, like I've observed that, and I could have an algorithm that is like, oh, I'm like here. And how do I get sort of the graph? How do I make this graph around this vertex? How do I get the correct graph around it? And it's like, well, I guess I had two vertices, right? So, and the way we could write this is as a pattern that matches on the graph, where we are like, green is the point we're expanding. Black, but there's no black here, is the things we're matching on. So this like, this just basically means we have the green thing and it has 0 outgoing edges. And it's like 0 connections to other vertices. And then we say in red what we want to add. So here we just add 2 of these things. And then we would get this subpart here, right? We start with this, and then we expand, and then we, by applying this pattern, and we
Okay,
get
so
that.
you can have these graphical rules and you can have a precedence over them.
Exactly, precedence is just the ordering. It's just like we have just a list of these, because so like this would actually now do nothing anymore, because it never matches again. Because you never again have a single vertex with no edge. So you add the rule that we match a vertex and it has one edge with the vertex, though we could also write this without the vertex, which I'm not sure ever makes a difference actually. And then say we add this thing, and now we would create this here, and over this would create this.
Mm-hmm.
By having the list of these two rules. And what I want to do is have like, this is a really nice representation, right? You see exactly what's sort of going on, what the rule means. Whereas before it was like weird a bit. But it was a lot harder to see what's going on if you write it down in Lean 4 code, is what that was. And I would like to make the notation such that it can just construct any graph. And then the intuition is that, or like, well, I mean, notation isn't really necessary, but well, now you can really see how the algorithm sort of would work, and that it would be pretty simple, right? Or like, well, the algorithm for matching is really simple, right? I'm like, oh, does this match? Well, is there a vertex with no edges? Then this matches. Or here, if there's a vertex with the one edge, then it matches. So like the algorithm is like it's really trivial to like implement this, right? To match it and then do the substitution. And now the thing is, because of these patterns, like it feels like, I mean, like, okay, I was doing it before, right? I was like, oh, here I have a single vertex. What do I do? Like, so sort of imagine you start with the single vertex, and then you're like, aha, I actually know that here are 2 vertices, but like sort of like I'm mentioning, I don't know them. I don't know what they are. And then I'm like, aha, what's the pattern now? And actually, like, it's actually a bit sort of confusing. And I feel like this is like so simple that it's a bit hard to think about. Like, basically what we do is we have some graph, and we do BFS in the graph, and we can just compute what is the substitution route such that we get to the right graph, which seems like in this case it's just this, right? So if we have this, and then we're like, oh, what's the substitution rule? We are connected like this, but like obviously it's like just like this. These are the right things that we need to substitute in, right? Like it's just like, and then we do the BFS more. Let's make the more complicated graph. So we do this and this. I don't know. Like let's say we have this graph, and we start in the center.
Nothing happens.
No. Well, now we're doing the inference procedure. So there are a couple of things we're doing. There are a couple of procedures here.
I don't know why, like, I would... Okay, maybe I can now give my comment. So what I would say is this is nice.
Let me write this down. Like we have the substitution operation. Well, okay, actually I guess we have only 2. And then we have the pattern inference. Like that is used by the substitution operation. Okay, what's your comment?
My comment, this feels like grammars. like there's a whole like theory of languages, right? Which are like strings of symbols where you then replace like strings, substrings with like you have these replacement rules. And I think you can do the same here. You basically have a similar thing where you could say you have replacement rules. So this is a bit more general than your thing, like the example.
Replacement. Formal language. How's
It's
it
called
called?
just formal languages. Formal languages. Right. So regex is one example of this. Regex is a particularly nice behaved formal language class. Or it uses these concepts.
Is this also related to the finite state automata? Because taken a string, or is it a string?
So finite state automata is like characterizes all nice languages that you can check if a word is in it in like a very short time, which can be represented by finite state automata, where you don't have recursion.
Okay. So finite state automata is like every finite state automata checks whether a string is in a language. Like for
I mean, this is like one interpretation, but
okay.
I don't mean that like it's not the same. It's not necessarily the complete same, right? Because in formal languages, you define a language in terms of generating rules, but you want to do something like similar, but not quite the same. But basically, you want to have these replacement rules. We just have like a graph, and then you replace it by another graph, and you interpret these graphs as subgraphs. So in your example, you replace the subgraph with no edges by a graph with 2 edges and 2 new vertices.
I don't understand. Yes. So these are sort of the rules for what subgraphs to replace with what.
Yeah.
Yeah. That seems so related. I mean, I guess it's very weird if nobody had thought about this.
I mean, the formal language is different because there this would be equivalent in your graph example to say you specify like what is a line graph, and you do this by saying, okay, one single vertex is a line graph, and if you have a single vertex and you add 2 vertex, then it's a line graph. And if you have a line graph and you append 1 vertex, it's also a line graph, which is different from what you want. You want to like somehow take the limit.
If you have, can you repeat that? So like you were saying 3 rules of.
So in the formal languages, you have a language which is a set of strings, which are the words in the language, and here we could say, okay, we have a set of graphs, which are all the finite line graphs. And now we want to generate all these.
This is the language.
Yes. So it's not like it's analogous, but it's not the same. Because you want to somehow say, we have a limit. You do all these operations, and on each local world, like if you, at some point it doesn't change anymore and stays the same.
That's what you want to do in the formal language.
No, that's what you want to do with the graphs. You want to say, okay, the world is locally described by my rules.
Well, I mean, potentially not even locally. I mean, possibly not for all worlds, but is it for... So, obviously, in a trivial case, we can generate any finite world state graph, at least, like arbitrarily large, with like a rule like that, which is just, well, you just have one rule that replaces the thing with the entire thing, right?
Yeah, but that's finite.
Yeah, but like
I
arbitrarily
guess
large.
I think
Like
the
if you
first
allow the graph to
restriction
be
you would want to
infinite-
put on rules that the rules can't produce infinite graphs, right? That would be
the
like
roots
the
should
first.
produce infinite graphs. That's the whole point.
No, I mean in one step, that the rules are themselves not infinite.
That seems usually good. Yes. Like here's the problem. Like Chaitin's number is uncomputable, right?
I don't know what Chaitin's number is.
Okay, take some uncomputable number that
Yeah.
you can't approximate. like that number is sort of random. There is no compressed algorithm for it. That's what it means, right? Like if I do Solomonov reduction on the world that is just like this uncomputable number, sort of, it will be sort of a program that just lists out just prints all of the digits of the number. Make sense?
Wait, how does that work? Like, how do you define this that it works?
That what works.
Oh, okay. Okay, that's a very nice way to construct an uncomputable number. Okay.
It's the Haltic probability, right? Is it
Yeah.
also that?
Yeah.
The Haltic probability of a randomly sampled Turing machine. No, of all Turing machines or something. Yeah, the probability if I sample a random Turing machine that it will halt.
Yeah. And I mean, then it's very intuitive that this is not computable.
Yeah, it's pretty weird, right? Because I can't compute whether any Turing machine halts anyway, and now I need to do it for infinitely many.
And the weirdest thing is that this really exists, right? Like this is feels like a
Well-
very natural definition, right? It's like not some arbitrary real number that you don't know what it is. Like most real numbers are not computable, but this one is like actually like a real thing.
Yeah, or at least it's concrete. I guess it's a bit confusing for me to think how real it is if you're thinking about infinitely many programs. But I guess there are only countably many, so there are not even sort of that many. I think, but the interesting thing, or like, I wonder what happens if you say like, yeah, just took the first Google Turing machines. What's the Haltic probability now? Now it's not infinite anymore, but you still couldn't really compute it probably. At least not like in a nice way, right? You cannot do that.
I don't know.
Or
Depends on
like,
the like you.
like the algorithm for checking whether it halts. Would that algorithm literally like?
Depends on if this algorithm itself is smaller than, like if it is in your selected set of Turing machines.
Yeah, you only look at that. We are not allowed to have a really a different, or something that you might need to say. I don't know, but like if I give
I mean, you
any
can
arbitrary
definitely
Turing machine,
select. You can select all the Turing machines for which you can show that it halts, and you can, and all those where you can show that it doesn't halt, and then you can take the probability of that, and then I think this should be approx. This shouldn't be.
But it depends
you
on
can't
how many there
decide.
are where you can't tell. If there's zero that where you can't tell for some reason.
I mean, if you already would have this list, and you only care about programs which are like smaller than some number, then you have a finite list where you need to check it, and by construction, you can actually like find a proof for each of them, and then you can have a real probability.
What do you mean find a proof that they halt?
Or not halt, yeah.
Wait, what? But it's halting
I'm
problem.
just meaning if you already would have a list about problems where you can show that it halts or can show that it not halts, which you can't have because it's uncomputable, but if you would have that.
I see. Because there might be a program where the program that you have to check whether it halts would not work on it, would give the wrong result because it is contained in the program. Which is not sure many of these programs there are sort of, maybe there's not that many that are this sort of thing, but I don't really know.
I mean, for example, we can have one Turing machine for which we can show that it halts, and we can just have that set of Turing machine and say, okay, what's the halting probability for this set? And then we say it's 1, I mean. So if you make the pre-selection for programs where you can show it.
Yeah. Well, then you can calculate it somehow.
Yeah. Okay, so why did we talk about this number?
So if this number, well, the world state graph for any computer program, there is a world state graph. Or let's say differently. So like we can have a computer program. Like there's actually a computer program to compute Chaitin's number. It is just, I don't understand, but somehow it is like it's like sort of so bad. Like it's a bit weird. It's like I don't understand how to say how bad it is because I don't understand how bad it is. But there is sort of a computer program. You run it, and then it approximates this number. But it's sort of like it is like so terrible. Like it's like the worst. I don't know how to say. It's like getting closer, but sort of exponentially slower or something like that. I don't quite understand it.
But then it would not be.
It's just probably what you are saying. Like you could run the thing by like, yes, I'm just running all these Turing machines, and now I check if they halt, and then I'm like, yes, one more halts, that changes the probability. But anyway, that's not that important right now. But I'm pretty sure that's correct because Chaitin literally said that in the video, so that must be something like that supposed to be correct. But here I'm just wanting to say that we can have these random things. Like you can have a computer, like you can have Chaitin's number, and then it's sort of like there is no short computer program that does it, that computes the number efficiently. Like that's definitely the case, I think, right? Like because like you cannot, like if I have this random number, you cannot have this short program that prints the number, because short program is just to print the number because there's no pattern in the number that you could extract, right? Like, for example, if like a practical example sort of would be like, imagine I have like an image and now I run a JPEG compression on it, and now I run JPEG compression again on it, but now it will be like not compressing it. And that's not really how it works. But or like imagine a different thing. Imagine I have some lossless compression algorithm, and then I have some data and I run it on it, okay, and now I run it again. But now it will not compress really anything probably. Or like at least maybe like a tiny bit or something, right? Because it's now not the patterns there's no patterns anymore because they already got removed by the compression. And you can start with this thing that is just not compressible. And now here's the thing, it's like the graph can also have patterns in it, that's what you're describing here, but you could have a graph that would just be random. There would be no patterns in the graph at all. That's like a possible thing, right?
Yeah, you can have an uncomputable graph.
Exactly. And now I was confused why I was saying that. But somehow I wanted to say that thing, that this is in the graph. And then I think I want to say yes, then we could have the giant graph just here. Then we would need to do the same as in the computer program. In the computer program, if it's an uncompressible number, you need to say like, yeah, put this potentially infinite number in the computer program. That's the only way to do it. Yeah, but you can't
because it's infinite.
Yeah, if you say if a computer program is finite, then it doesn't work. Then you can only like have sort of an approximation, but it's arbitrary good. The same thing you can do here. That's what I wanted to say. It's the exact same thing, but with these graph patterns. Okay, yes. And so what we want to do is have the graph and then compress it. Okay, and now we are talking about the language and how that might be related. So how is that related? Maybe it's actually like, I think you were saying something before about what the interpretation would be if you had the graph and then you would say is formal language.
Instead of generating one graph, you would have a class of graphs, right? So in this example,
yes. So the graph would
instead
be
of saying, okay, we have
language.
Instead of saying, okay, we have the infinite line graph. If we like do these rules infinitely many times, we say each step generates a graph, and this graph is contained in our class, and our class is defined by these graphs. Mm-hmm. And then in this example, this means it's all the finite line graphs is the class of your class.
So we're saying C is the subtype of the graph type.
Yeah.
Which I don't know how to write.
You can write C subset graphs.
Oh yes, good to do that. That's what we exactly say. In set theory, I guess. Aha, okay, so we can, yes, probably if you would write it even in type theory, in Lean at least, you would probably just do this. Probably you could just say the symbol means subtype.
Yeah.
Okay, and somehow I think subtype is nicer because the subtype is containing the property actually. So we need to be more specific.
What is a subtype?
It's a line graph.
The subtype is just... Wait, what was it? It's a function from graphs to prop.
Yeah, so subtype, it would be like subtype graph. That's that's a carrier type, I guess you could call it. And then we have a function which would be like is line graph. This is the argumented dot. You can just write. This is actually relatively.
Yeah, I know. This is something I like very much about Bean, that they have all these nice mathematical things that you use in maths.
Yeah. Okay, so this would. Well, okay, now it's actually clear what it is. Now I don't even need to say anything anymore. the type says the thing. But I guess the problem is that you actually need to say it. You cannot not say it. Or something like that. Okay, but we have the C, and now these are the graphs that we care about, and you're saying like we have some algorithm, let's call it, I don't know, gen. We have this gen algorithm which takes in patterns, returns a graph. That's it. But for like no, it's more like it takes in the patterns, it takes in a graph, and then takes in and then returns a graph, and then it's like this is like one step, iterating one step. And so now we can actually say something like, if I have sort of like, I could say like gen, and then I say sort of like, well, let's say this pattern is like P1, so say gen P1, and we would get in some graph which is sort of like, is singleton graph a thing, a word? Singleton graph, what's the graph with one vertex? Well, let's just call it the one vertex graph.
Yeah.
Wait, this is actually a bit weird, because okay, if I do that and then one vertex graph, well, this obviously of type, well, let's say this is our type, then this is of type C.
What is the subtype graph, right? Okay, it's of type C.
Yeah.
I mean, it's like, I don't know how subtypes work, but it's like first a subtype graph, and then you can, by the definition, show that it's of type C or something.
Oh, I see. Yeah, I mean, obviously because it's a subtype, it's like, it's sort of more constrained, right? If I say, like this would actually say as I return a graph, which is right. But
I'm not sure if that's really how it works with types. I think maybe you need some
yeah, exactly.
coercion.
It's like this would say I'm returning a graph. This would not say I'm returning C. This would say I return a graph, which is correct. It's because it's a graph. And somehow we want to say this is graph though is always C. Like what?
I mean, the
like
thing
theorem,
is, like C is defined
is
through P1, right?
No, this is C. It's just a type.
Oh, I guess in this line graph you can define however you want. Yeah, and then you need to prove it, I guess, right?
Yeah, so we say just theorem. Theorem.
Gen P1 takes graph to line graph, which is not true. So you have that this is of type C, which is like weird. Which, because it's already of type graph. So you have to like convert it. And I think you do that by showing that it's a line graph. I think that doesn't work. But it doesn't matter, like mathematically, like we don't care, this like type theory.
You could just say it's line graph.
Yeah. And then you can construct like a representative or something of the subtype, I think. Yeah, I think then an element of LG is a graph plus a proof that it's a line graph, right? So basically now...
yes, exactly. It's a proof that this property holds on. So like actually subtype is like the type is parameterized by subtype. We get some type alpha, and then we get some property which is alpha to prop or something, or bool. I guess I don't understand how that works exactly. And then we say, well, we get something of alpha because it's actually just a structure. Then we have some alpha here, and then we have also some proof that alpha. Well, let's call this let's call this F. Then we have a proof that F of alpha.
Right. So it's basically
no, wait, this is all wrong. This is all wrong.
So no, this is a product alpha times
A.
F alpha, right?
Yes. Well, F alpha, but well, it's a product where we have some like we have.
So
like,
this
is a
gives us a
tuple.
new
This is a
new
tuple
type,
of.
which is alpha times f alpha or fa.
But this is basically the same as alpha times.
I think you need to name it,
Okay,
so
wait,
it's
now
weird.
it's a bit confusing.
Yeah. Yeah,
Can't
it's
do
like
that later.
named, so I don't think it works. It's like you need alpha a fa.
Like the thing is, we want to say this is a proof here that f holds for a. It's
Yeah.
like the subtype is like the idea is sort of like here's the type, and then we can sort of this describes the elements of the type, right? It's saying like if I have some graph, here's like some graph, and then like to construct an element of a subtype, you're like, yes, I want to construct, please, the subtype of is a line graph. To do that, I'm going to provide you with a graph and a proof that for this specific graph, it is a line graph if f is a line graph. That's how that works.
Yes.
And then that's like, well, all the things you can construct now are exactly the things that are graphs, and I can prove that this is a line graph. These are all the things you can construct. And you cannot construct the thing where it's not a line graph.
Yes.
But yes, you can't write it down as a normal.
It would be
product
like a
type.
dependent Cartesian product, which I'm not sure if this is like a thing that's standard.
Yeah, definitely you can't write it with the normal product notation. I mean, I guess you can. You would need to write it just like it's written here. You need to say a is alpha, and then times f of a. Like only where's the f now? But I guess, it kind of doesn't work. Still doesn't
No, it
work.
works. You just write
No,
it.
it doesn't work. Because like we need to say we want to call this function. We don't
No, it
want
works
to write
because-
the type.
You just write instead of where, you write equal, right? You write subtype alpha f alpha to prop equal to.
Subtype alpha f. What? You mean this notation? I mean, we can do this actually, maybe with this, if we would write something like we have another thing, f alpha to prop. Possibly this just doesn't make any sense because I don't know what I'm doing. But if you have the triple
No, this
thing,
doesn't.
and then, but otherwise you cannot say f of a. Where's the f otherwise?
No,
It's
but now
f of
you
a.
specified all the subtypes. So what subtype is? It's a subtype is a function which takes a type and a function and gives you a new type.
I know.
Right. So you just
Okay,
write
but then
subtype alpha f
Yeah, but that
equal
was just
to.
okay. That's what doesn't make any sense. What I was doing anyway. I was just like, how can we write it with normal product notation? The answer is you can't.
No, you can.
No,
Like this is correct what you wrote. I'm not sure
you're
if it
right.
works. In,
this is wrong. What I wrote, but what is
no,
right?
that's correct.
But where's the f?
The f comes from the definition above.
No, we don't have that. I'm just doing this definition without having the above one.
Then where does alpha come from?
No, alpha is just like an arbitrary type.
Yeah, and
That's
then
fine.
f is an arbitrary function from alpha to prop. And then
Yeah,
you
but
don't
you
have a
didn't say
problem.
it anywhere here.
Yeah, but you also didn't say what alpha is.
Yes, though that seems different.
No, I don't think so. I
agree.
think you just need, instead, just write equal before, and you're done. Just write subtype alpha f equal to.
Yes, I agree. You're right. But only you would literally just. But you would literally, yes, you would write def subtype. Def subtype this entire thing. Wait, would you say def?
I don't know. just implementation details.
Yeah, you could write a function and then you say like, yes, a function is subtype, type it this, and then return a type, and then this is the type.
Yes.
Okay. Yes, I was trying to, without this, write this. Don't use this.
I don't know what you want. This seems
Yeah,
like
that doesn't
if you
make
know
any sense what I
and
wanted.
f, if you know alpha and f, you can write it. If you don't know, then you can't want to write it.
Exactly, something like that. Okay, but this was a really sidetrack. I just want to say we have. Okay, what you want to say is like we have the subtype of LG, or like we have the graphs of the specific property, and we're saying like this function generates all graphs of that property, which is actually just wrong because this does not do that. What I just said. I'm not sure if that was what you said before. But this pattern doesn't necessarily generate all. Actually, it doesn't. This pattern does not generate all line graphs because it never generates a line graph which has 2 vertices.
Right. Okay.
But this is actually not what I sort of care about. I'm like, though I mean, actually you could just remove this and now it would, I guess, oh wait, it still not work. But like, I'm not sure this is like really that important. Like the important thing is that we want to compress a graph somehow, because compressing the graph is literally doing program inference, because a world-state graph is just a program representation. So compressing that's the same as sort of doing Solomonoff induction in some sense, only like good, because we can now locally sample some program and then compress that part into this description of the graph, which is really small, which means we have a description of a program that is really small compared to what we had before.
Don't think I quite get that.
So like in Solomonoff induction, we're trying to do this. We are like, I have all programs. Please like select the programs that are compatible with what I'm seeing, right?
Yeah.
And
now what
that's
do?
not what we do now. We don't start with the programs, but instead we just sort of observe the program. Like you can take any program, then you unroll it, right? Like in Solomonoff induction could be like, yes, here is all the programs, the infinitely many programs. For each of these programs, there's a world state graph, right? Like world state graph just like describes the program.
Yeah.
So what we can do instead now is sort of like, I'm in a world and I take one step forward. Okay, now I get a world state graph, which is this, sort of. It's like, or like if I moved forward, then it's like, I move forward, I move like left, I move back, I move right. Oh, I ended up in the same position. This is the thing I observed now. Now, if I have sort of now not the source code, sort of, but I have the world state graphs, I could be like, okay, what world state graphs don't have this pattern? Well, clearly they can't be the world I'm in, right? That's how you would sort of do the Solomonoff induction analog. That's how you could do Solomonoff induction with like this graph analysis. And that's sort of not really what we want to do. But it's sort of, well, I'm just saying sort of like we could literally, I mean, I think in some sense it feels like this is a lot better than the Solomonoff induction, because we know exactly sort of why. Like it's not more verbose. It's like, yes, look, this world tells me there's a single vertex. I can't do anything. I'm always gonna, maybe there's a self loop, always gonna go to the same thing. And then I observe this, and I was like, well, obviously, well, you don't even need the second, that's the first step. It's like, oh, this world's, well, clearly it's not this world. Because in this world, I couldn't do the thing that I just did. So you can just write Solomonoff induction such that it would work with this graph thing. But we don't kind of want to do that. We want to do something better. Instead of sort of having the entire world state graph in the Solomonoff, like in the Solomonoff induction, we have just like infinitely many of these world state graphs, and we're like, oh, which one is the right one? And that's what we now not do here. Let me actually take some notes about this, because it seems pretty good. Solomonoff induction and world state graph analysis. So the thing is that every world state graph represents a program. This means we can rewrite Solomonoff induction by expanding out all of the programs in the universal prior to be world state graphs. Note that this is not practical, of course, because they are probably almost all infinite. Then we can filter out world state graphs based on the world state graph that we have generated so far in our world. For example, if we observe that if we move right, down, left and up, we end in the same world state, we can exclude the world that contains a single vertex with a self loop, because that pattern is impossible to observe in this world. Okay, so this is about like Solomonoff induction can be done by world state graph analysis, or rewriting Solomonoff induction to use world state graphs. Okay, and then, but here's the good thing, because this is still terrible. we can do something much better, I think. So like instead of doing that, where like, well, that's obviously still completely interactable. But what we can do now is, there is this mechanism that doesn't exist in Solomonov induction of, it's easy for me to generate sort of, like to analyze some structure. Like Solomonov induction doesn't know anything about extracting sort of structure on the world, except in this like really brute force way. But if we have the world state graph, it allows us to extract the structure in terms of the transitions, sort of, that we can perform in the world, if we only assume that we can compare two world states. Like if we can compare vertices in a graph. If we have that, we can analyze the structure of the graph.
You're assuming that the world is in a particular way, and then you can do something better than Solomonov induction, which is fine.
No.
But you should be aware then that's
I
what you're
don't.
doing.
No, I don't. I'm just set. I only assume you know that you can compare vertices, meaning world states.
Yeah, you assume that you have vertices.
Yes, I'm assuming I have world states. I mean, doesn't seem
Yeah, I
like
mean,
a very unreasonable assumption. I'm not quite sure what this would mean to have a world where the world couldn't have any states.
No, but your world states are like have only information content in the way that they relate to other world states, right? A typical
I can have
computation.
more, but I'm saying like this is a good feature of the thing.
A computation that holds is just a string of world states like this that have, right? Or what kind of?
You can't think about it like that because, well, there is a bunch, and I think a Solomonov induction actually would possibly have the same problem. But basically, to generate the world state graph in the first place, you need to sort of assume that you're a Cartesian agent, I guess. But then definitely works. There might be a way to formalize this
But what's the world state graph of Solomonov induction?
Well, every program has a world state graph.
Yeah, but it's a very boring one, right? It's like a line.
Yes, so like if you have a deterministic program, it would be like this. But what I'm imagining is not this graph, but I'm imagining there is some sort of special thing of the agent. We don't have the graph that is just only the world, which is deterministic, which just runs deterministically forward, and it's either a line graph or it's like some loop, or it's like either it's like a finite line graph because it holds, it's an infinite line graph because it doesn't hold, or it's an infinite line graph because it loops. That's the only possibilities. But what I'm mentioning is this program is sort of a bit special because there's a function that is ask agent, and sort of this agent can say anything, sort of the intuition. Like the agent returns what action to perform, and that's how we get sort of the graph, right? If I have a grid world and I can like move in the grid world, I need there's some input, right? That the agent does something. That is a thing we need now. Otherwise, you cannot really talk about this world state graph. That's an assumption that we need to have to generate it. This is like the assumption is basically you can do an action. I mean, I'm not quite sure how strong this assumption is. It seems like maybe it's not that strong. It's just that
it's fine.
I can do an action, or I can do this other action, or this other action. Actually, I'm not even sure if you need to do that. I'm not even sure you need that assumption. I mean, the only thing you really need is that you can compare vertices.
So actually, it's not like see if you take repeated action, it's actually not a line graph.
But the thing is that it's a line graph, it's a deterministic program. Now it's not deterministic in some sense.
Because you have the agent that does actions.
Thinking the agent could do anything.
Yes.
I mean, the agent, at each point, the agent will actually do just one thing, but sort of in the world model, so like the agent would never observe itself doing multiple things at the same time. That doesn't make any sense.
No, I think that's correct.
Like the agent can only traverse one edge, but that's probably a kind of important point. It's like the agent can only ever traverse one edge in the world state graph at a time. However, we want to think of, or like in the model, like there's some sort of model of the world. Like we want to create a model of the world. And in that model of the world, we want to think about it like the agent could have done all of these things, like because this model of the world should map out the possibilities of how my behavior influences the world. So However, in the final world model we are constructing, we want to think about it as the agent could have done anything such that we can use this world model to calculate what effects particular actions we would do would have on the world. We need to be able to compare vertices in order to generate the world state graph in the first place. But that's the only thing sort of you need to do actually. I don't think you need anything else. If you can compare world states, you can do it. We can formalize.
The question is just how often you will end up with a world state that's just a line or like a tree. So basically a line, because no matter what actions you take, you will never get back to anything you did before.
Well, it will. What do you mean? Like, I mean, if that's
Like
the
in the
world,
real world, there's no action that you will get you back to the global thing that's the
Yes.
same, right?
I think.
So you need to.
I think this is some sort of thing that needs to be solved, but doesn't seem to bottleneck to me right now. Like, if you could solve, I mean, we don't know how to solve this in the world where, like, the problem with that is that the world is not such that the agent's action is sort of the only thing that influences the world. That's sort of the main problem there. It's like, oh lol, the entropy increase in the universe can never go back. I don't think that problem is sort of the bottleneck.
I mean, I think
sure if
that's
what you meant.
probably a bottleneck at some point, but it's okay to focus on the.
I'm not sure
like,
that's a bottleneck because humans didn't even know what entropy is for most of the time, but they could still analyze the structure of the world.
Yeah, but you're trying to formalize intelligence and not.
Yes, and not sure it's required that this intelligence immediately sort of like, so basically I would not be surprised if this problem is literally solved by having bad sensors. It's like, oh, I cannot observe quantum physics with my sensors and notice all of these like weird things that the entropy always increases or something. And therefore, like, I just see some patterns and then I say, oh, there are patterns, even though they are not sort of like exact. They might be at the level where I'm observing them. They are
basically
patterns, but
basically you don't require things to be the same. You just require them to be approximate the same, and at the beginning, and then you're done.
Yeah, like that seems like it might just solve the problem, and if not, it seems like it just doesn't seem like it seems like making your pattern sort of yes, and I'm detecting approximate patterns, or just being like yes, I'm observing it at some high level. That doesn't seem very difficult. Okay, so this is about.
Yeah, I'm not sure, but.
I'm also not sure, but I'm pretty.
But it's okay to ignore it for now.
The bottleneck right now is not, says my intuition, to figure out the following problems. In the real world, the environment can be such that events other than the agent performing an action influence the environment. For example, in Minecraft, the pig walks around. In the real world, you can never return to the exact same state you were in before because entropy has increased. Some intuition for why these problems might not be that important right now are that this problem might be solved in large parts simply by having not super accurate sensors that observe all of low-level physics so that you wouldn't even notice that the entropy has increased. Also, you could do something where you do approximate pattern matching or just ignore certain features in the environment, or potentially do something where you could discover the regularities in the graph that are still there despite some specific things changing. For example, if we had a grid world where we had an additional variable which would just increase by 1 for every time step, instead of a 2-dimensional lattice, we would now have a 3-dimensional lattice. But we can still notice that at every possible step we have just this 2-dimensional lattice. You can still have this model that describes this world and models the fact that you can never go back, while still making it such that this model allows you to just normally plan in the squid world of where to go to a particular position. You can't return to the same world state. It's not the bottleneck. Okay, but the thing I wanted to say about Solomonov induction is that, like, we can analyze the structure of the local graph that we have generated so far. And you can't do that in Solomonov induction. You can't be like, look, I know what the program is. Like, you sort of like, if you look at some part of the world state graph, you know what the program does sort of here, right? It's like
Well, I can't just put it
Solomonov
in
induction.
Solomonov induction.
Solomonov induction doesn't do that at all. Solomonov induction is not like, I'm observing
think
this
it does
pattern
it.
in the world. What?
I think it does it.
No, it doesn't do it at all. It doesn't look at the local structure that you have observed. And
No, it does.
No, it does not. Okay, why do you
If you
think
have
it
a-
does do it?
Well, if you have a loop, then you condition on this, then you exclude all programs which don't have that action loop.
Yes, yes, you do it in this way where you're like, yes, let me just like do it's an infinite amount of computation to filter this infinitely large list after I've computed that these programs also halt. Then I do it. Like, you do it in this, but what I'm saying is it doesn't do it in this way where it's like, it is not constructive.
It's just
It is,
construct.
it is not constructive. It's not like, look, I have the structure. What is the structure? That is my world model now. That is the part of the world that I'm modeling like this. Look, so like, as we have generated so far, like, so the Solomonov induction could be said that it analyzes the structure by doing the operation of trying to match the structure with all of these infinite hypotheses that it has. That's not what I mean. I mean, what we need to do is look at the local structure. That tells us that the program looks a certain way at this particular position. And therefore, what we can do is take as our hypothesis that at this particular position, the world is structured like this, without doing any exhaustive search at all. It's like basically the whole thing that Solomonov induction does, yeah, we just don't do it, still works. Or like that's my intuition. It's like we do the same thing that Solomonov induction does, but we remove the exhaustive search.
I don't know. Like you're basically capturing one aspect which you can, where you can conclude a
What do you mean
particular
one
thing.
aspect? If you find the entire structure of the thing, it's the same as the program. It tells you everything about the program. That is the world. It is the same. It's like you have complete information of the program now if you had
Yeah,
the
but
entire
the
world
point
graph.
about Solomonov induction is exactly how you generalize outside of these loops, right? That you found.
That's a good point. Yes, I didn't talk about the extrapolation yet. But obviously what you would do is like, I observe the structure here. I'm seeing this pattern. Look, the structure has repeated a bunch of times. It's going to still repeat. Which is not trivial to do, I think. But I think you can do something like that, and then it will be significantly easier than what Solomonov induction does. I mean, it should be kind of intuitive that you can do something better than Solomonov induction. Because certainly the human brain doesn't do Solomonov induction. And I can detect structure
So
in the
well,
world.
you mean better not in terms of outcomes, but better in terms of being actually efficiently compute.
Yes. Okay, I remember. It's about that it's like note that if we can make a model of the entire world state graph that actually describes reality, then we just know basically exactly the program that describes reality. So
I'm gonna
that sense it
return
is-
with my phone
okay.
and go.
Okay, so like the important thing is that if we get an accurate model of the world state graph, we're done, right?
I mean,
Like
then
the
you have
world state.
yeah, then you have the world model.
Exactly. So like if we can do the graph analysis such that we get this model by like finding these patterns, like that's right what you're saying. We need to extrapolate. Like Solomonov induction does do the thing of Occam's razor in terms of like the length of the computer programs. And that's how it can generalize, because the real-world model is of course way too large, you can never do it. But I think you can basically do the same thing with the graph analysis. It is sort of a bit built in, that the Occam's razor thing. So okay, let's write. Yeah, well, I can explain in a moment. The thing is, so far we have only captured one aspect of Solomonov induction, of that we would correctly describe the local structure. But the good thing about Solomonov induction is that it formalizes Occam's razor in terms of program complexity, such that shorter programs are more likely to describe the real world. And that's what allows us to, even though we haven't observed all states of the world, make predictions of what will happen. It seems that often when you find structure in a graph, you can simply assume that this structure will continue to repeat, which gives you a similar kind of
I don't know what
Occam's
that's
razor.
supposed to mean.
So
What does it mean for a graph or for a subgraph to repeat or something? Whatever you
it is repeating is not the right term for saying this. I think the thing we want to say is you have a graph, and the graph is generated by a function, what we were talking about before. There's some generating function. For example, we could say this pattern matching notation is, like, what is the complexity of the pattern matching notation that describes the graph such that it will be constructed correctly? If we just say, like, there might be multiple pattern matching things that match the thing that we have. For example, there's the thing of, like, yes, I just have one graph, which is just the entire graph I've observed so far. That's a lot more complex than the actual minimal, sort of, if you think of the, like, for example, for the line graph, right, that I could make, like, yes, I have a line graph, it's like 1 million nodes. I could make this as a node. But that's not the smallest pattern that generates the thing. So you can think, yeah, what's the smallest pattern that generates this graph? And that seems really good. And it seems really natural to do that. So, for example, if you have a line graph, and we think about the pattern matching notation that would construct this line graph, that would contain the fewest patterns, then that gives us this kind of inductive bias. Okay, and now here's a really nice thing, I think, which is, like, note that in the pattern matching notation, the way we constructed it, at least in the one example we walked through of constructing a line graph, we can potentially just read off, as we do some sort of BFS search through the graph, what kinds of new patterns we need to add to describe the newly observed structure of the graph, in such a way that we are only ever adding the minimum thing necessary to describe the new patterns that we see. This probably doesn't work in general, because the world model that we have for generating the graph ideally should just work to generate a graph from any possible starting vertex whatsoever, or at least any very small subgraph whatsoever. Another problem is that if we always just patch up our current patterns, we could run into the phenomenon of epicycles, where we just are in a situation where, because we greedily updated our policy, we have updated into some local minimum that's incorrect, and we would need to scratch a large part of our theory and reinvent it with the new evidence we have in order to find again the simplest patterns.
Hello?
Hello. I was just writing this down a bit better. So does it make sense? I think this captures lots of important aspects of Solomonov induction. Oh, well, I mean, I didn't figure it out yet. But I think it's clear that it captures some. aspects, and I think you could make it capture other aspects that we care about. Like, I mean, yeah, I think this Occam's razor and pattern matching makes a lot of sense. Like,
Yeah,
that's
no,
the
I
thing
think
you can do.
like this doesn't really work. I mean, I don't really like I didn't really like follow everything. But to say we repeat the world graph, or to say we take the simplest rules that generate the thing, that's like Occam's razor. Like that's your equivalent of Occam's razor. And I think that's doesn't this have the same issues as the normal Occam's razor?
What's the issue with Occam's razor?
Oh, with Sermon of Attack.
What issue is
Well,
that?
basically, how do you what? I don't understand how you go from I've recognized these loops in my graph to this is how the graph continues.
So you
Also, I
infer
don't
the pattern.
actually-
So you infer the pattern. The simple idea is you infer the patterns which describe the graph you see so far. You're like,
Okay, so you want to like somehow get the smallest generating function, right?
yes. And
But
then
how
you're
do you
like,
do
yes,
that?
now continue. Yeah, okay. So that's what I want to do here. So like for this thing, so imagine we have already some graph. So we have this graph. And now we say, okay, we start like at this black vertex in the middle. And now we're like, oh, I don't know any patterns at all. I don't know anything. Like I have generated, so step one. Step one is like generate a world state graph. But just by like, well, imagine just move around randomly or something. That is not that important. I think you can do that. Generate the world state graph, like some world state graph.
But are you drawing somewhere or?
Oh, I'm writing this here. For example, in the simplest case, just taking random actions might be sufficient, though we can do more sophisticated things. It would work for very simple worlds, at least. Okay, and now we are like doing a BFS. We will say, well, we are like, okay, we look at this, and this, and this, and this, and this, and this.
Are you
are
assuming that you can go back?
No, we already have the graph.
Okay, you have the graph and you have the starting node, and then you do breadth first search. Okay.
And now we are like, okay, what pattern here would describe? I mean, actually, it's a bit kind of ridiculous, I guess, because what we literally do is like, we have the breadth first search. Well, that's our pattern. So like this would give us. The idea is that this gives us something like, okay, our pattern is we have some vertex in the center, and we have these vertices. I did it incorrectly because these vertices would this be red. So then we're like, oh yeah, we have here. We start here. What do we do? Well, we add these vertices here, exactly like this. Make sense? That's just a BFS graph. That's just a BFS graph where we are like.
Yeah, okay, the first step works. In the second?
Yes, now the second. Let's see if that still works. I'm not sure. So we would be like, okay, BFS from here. What do we do from here? What is the pattern here? Well, I guess here's a vertex, sort of, and then here's the vertex, and then we want to add this new vertex. So if you think about the BFS from this node, it would look like this. We have some center node, and we have this node connected over here.
But you somehow want to find a small rule, right? You don't want to just take the rule, okay, I have this graph, and then I have the next step of the search graph. This wouldn't generalize.
Why not? I mean, yes, I know this wouldn't generalize in general. This wouldn't generalize because if we start at this vertex and we have only one vertex, well, doing that's definitely wrong. And I'm just trying to do the simplest thing right now.
Basically, you want to find the simplest rules that generate the graph you know, like somehow,
yes.
And then you want to continue these rules.
Exactly. Yes, that's the idea.
And from any graph or something?
Well, how about this procedure? For every vertex in the graph in G,
I think you have to also know which vertices will have, which are partial nodes and which are already complete.
Yeah, we blacklist. We only match once. Oh, I'm not sure if that's what you mean. Okay, but for every vertex we do a BFS search and then check what. Well, I guess I'm a bit confused. Do BFS search and then have the BFS search of depth 1. Well, okay, this is not the procedure I did so far. We repeat this procedure for every vertex. So actually what we do is like pick some arbitrary vertex. Do a BFS search of depth 1 for this vertex. Create a pattern by having...
Couldn't the rules be invariant or something? I don't know. Like how...
I don't know what you mean.
But like, do you have this like selected start vertex, or do you want to like? Are you allowed for to have a starting vertex? Yeah, I think you are allowed to pick it, right? So you don't care about where you start.
Yes, right now we just pick an arbitrary vertex V. I have written it in the Google document, which you have access to. I can send you the link again.
Yeah, I think you should first be clear, maybe you are, but should be clear about what you try to want before you try to find an algorithm for it. And what you want
Yes,
is
I want to find the patterns in the graph that generate the graph. If I apply the pattern, the construction algorithm that uses these patterns in order to match on the existing graphs and then substitute it in, and then if I just repeat the
but you want to
procedure,
find
I
a
get
very
exactly the
good
graph that I have.
right? You want to find a very simple pattern, right?
So you have just want to find any graph.
Any graph is easy. You just have the first.
Yes, any graph.
The first node, and then you have the graph.
Yes, anything that's not like the degenerate, anything that is like that I can do that is simple that I haven't tried yet, which is I think what I'm doing right now. And I could think 1 million years about what's the exact properties of this algorithm and then not actually think of the algorithm, but I could just try to make an algorithm and see how it fails. And then, then it gives me lots of evidence. I don't know. Maybe it just works, the simple algorithm. It would be really dumb to think very long about what I even do if I just try the simple thing that just works.
I mean, the main question is, what does that mean it works? But of course, if you want to find any algorithm, then...
Yeah, also we don't need the simplest one, right? If you have like, yes, okay, we don't find always the exact simplest one, but it's like, lol, we can play Minecraft with it. Well, but it'd be a bit weird to say, yeah, your graph is actually like 2 bits too large or something, your patterns.
My intuition's very different from that. My intuition is that you first need to get to the abstract properties, and you try to approximate them, and then something just works because it relies on principles that are well understood. Even if you don't find a theoretical optimum, you do an algorithm which is inspired by the theory. And if you just find any random algorithm, I think mostly that's
okay. Once you have that proper abstract property, you could think about it now. I do this, you think about it, and then you tell me what it is. And we see who is faster, who makes more progress. Let's go. Okay, we want to check if we construct the graph based on the patterns so far that we have created with this procedure, if we can actually generate the graph correctly, or like if we get the correct graph. And then it's like...
Ich komme wieder auf den PC.
at places where we are not generating the correct graph structure, repeat the pattern inference algorithm above to insert a new pattern such that now the graph is described correctly. Okay, this is a very high level algorithm.
Und irgendwas rausgefunden?
I think, yes. This is what I got. Did you make progress?
I didn't find a good criterion, but can probably approximate the complexity by saying how complex is each, like how many patterns do we have, of course. So basically it's the sum over the complexity of the replacement rules.
Yes, that's what I was thinking too.
So that's the first thing. And then you can probably as an approximation just count the vertices.
Just count the vertices and edges or something.
Yeah.
But okay, but I basically knew that already. But I think maybe I didn't communicate it correctly, but that's what I was thinking about too. Yes, I probably forgot to actually say it, and also I wasn't explicitly having it in my mind, I guess. But or maybe I now have hindsight bias. But didn't I say that? I thought I said that.
I don't know. Maybe.
Just have the complexity of the patterns. Let's see. Did I maybe have even written it down. Let's see. Yes, I said we want to have the fewest patterns. So I guess I'm not.
Yeah, but this is not what we want.
Yeah, I'm pretty sure when I wrote that I actually meant the fewest, like the lowest complexity patterns. But yes, that's what you said is definitely the thing that we want. It just feels like, like it just feels very unnatural to say like we have this graph. Yes, the way we describe this graph is just to copy the entire graph. That's obviously what we have. It feels like it should be easy to not do that. If you're thinking about the graph matching. So yes, I think that is the criterion that we want, what you say. I mean, yes.
Huh? Oh, so you should read.
And here's some algorithm that does something that seems like maybe it goes in the right direction. Practice, but let's assume for conceptual clarity. Because we want, ideally, that our graph generating procedure can generate the correct graph from any possible starting vertex.
Maybe let's try the full lattice graph in 2D. I think it works for that.
I mean, I have not tried the algorithm at all. I actually don't even have a good intuition of what it would do. So that would be, I guess, now the next step. I want to run the algorithm on a whiteboard such that you can see what it actually does. So let's do that. So we have some words that graph. Okay, let's do the lattice. We have a starting vertex. Let's assume there's some underlying graph G now. So we have this arbitrary starting vertex here, and now we do the BFS search for size 2, which would of course be this. This is better BFS 2, right? Probably it breaks, I have a feeling.
Yeah.
And now we do the additional. So that's actually what we generate, which you can just immediately write down this graph. And now we say we add a bunch of edges, specifically we would get this, right?
What is that?
Replacement graph. But this doesn't work because there's a problem in the lattice. Because the way I've was doing the notation so far, it means that if there's a vertex and there's 2 incoming edges, it means it needs to have exactly 2 edges. So this kind of structure, if I'm starting, like let's assume we have somehow generated this structure here. We have it. Now we add this. Well, now the structure is not there anymore. If you understand what I mean.
No.
But here we are saying we're matching at some vertex, and this vertex is such that to the left there are 2 vertices, to the right there are 2 vertices. If I have added the red vertices and I'm matching, let's say here, then I'm like, to the right are like 2 vertices. That actually works, but to the left the vertices are different, because here this vertex is sort of only has 1 connection, but if I'm looking here then this vertex has 2 connections, and so it doesn't match. But what we could do is we use a different, there are multiple things we could do now. One thing is to use a special notation, which is we can write this. Triangle means triangle 2 edges means it has at least 2 edges. Then this would work, I think. Actually, I'm not sure. Would it work? So we could definitely match to the right now, and then we would sort of generate this graph, which is wrong. So we could definitely generate the wrong graph, which is of course dumb. The problem is that these 2 are not connected. That's wrong. But I think something like this algorithm is going in the right direction. We want to do some BFS unrolling, and then discover a certain structure, encode the structure in the replacement pattern, and then like continue that. If we like, I mean, this was actually in the first step of like, Actually, this algorithm might actually just work. Actually, what I was saying that doesn't work is kind of wrong, because the algorithm is not finished, right? This was just the first step. We could now infer a bunch of more of these patterns until we have enough such that it does work. The question is if that would be the case. Like, mention of the red letters now. And, and now here we get 7 here.
I don't know. Maybe write down the rules, because I think it doesn't work.
What do you mean the rules?
The
That's the
replacement rules.
That is the rule.
Yeah, but that's exactly what you not wanted, right?
Why? It does the correct thing for the first step. No problem. The problem is it doesn't match. Any other thing afterwards, like that's not a problem in itself. So we just now infer what is the next thing we need to match. So we get
No, that's a very big problem.
No, I don't think it's necessarily.
Lattice graph is the most regular thing.
Yeah? I mean, I think the most regular thing is probably things that are more regular. The empty graph, the graph with a single vertex, the graph with... Well, okay, it's probably the most regular thing.
And if your rules are like very weird for that already, then it's not.
I mean,
a
the
good sign.
a complete graph is really regular, I guess. That's probably.
But a
simpler,
complete
actually.
graph is not infinite. I mean, of course, you could have an infinite one, but that's like not possible to get by rules.
Let's just do this algorithm here. I think it will possibly work. I think the weird thing is, like, where do we do the BFS now? I think we want to... I guess in the actual algorithm we just said pick a random vertex. Maybe we do something where we go out. So maybe we want to do something now like... So we have a starting vertex. To compute, or like, well, okay, it's a bit different. Next vertex. I don't know. Terrible name. We want to do something like... After
I think before you do
the replacement pattern,
I think you should first find the best pattern of the regular graph, of the lattice, and then see how you could get that.
Yes, I tried to do it yesterday. I was literally using this algorithm. Intuitively only. But I think the thing I did yesterday when doing that, I didn't actually get to the thing where I had it completely. But it was using something that was almost this algorithm.
Like if the lattice graph is not very easy, then then everything is wrong. Then you need to like change the definitions a bit.
I don't understand what you mean. It's not easy. It's why would it?
Like the lattice graph, which I have should like 2 simple roots or 3 or something like this.
Not sure that's correct, but you can do it in a moment. Okay. We do a BFS starting from to determine the next vertex to compute what pattern it should unroll into. Like, I think it might work. It's just like we didn't execute the algorithm yet. It's just step 1.
It doesn't work.
Okay, but we can think it will work, but let's think of then the algorithm. What's the optimal pattern to describe the lattice? So let's see. So let's say I'm looking at, so I think you could do something like this. Let's just assume we're starting with this like 3x3 lattice.
Yeah.
And so our replacement graph, well, I mean, we can actually also say if we have a single vertex, and I could literally just say like, here's the thing. Okay, and then it would be red.
I think it actually shows a fundamental problem which we need to address. So what I would say intuitively, to get to the next step, we extend all the edges, and after that we extend the corners.
Yeah, exactly. Now I would do something like, oh look, we wanted to match at this vertex, like where we have sort of. Well, now I drew it like this. Let's do it at the bottom because it's the same. I think we could do this thing, right? And then we say we add a big cube below, and this would match over here. But actually, it wouldn't. It would only match if we sort of add additional edges over here. So if we do that, so we start with this, and then, because for these patterns, now we're gonna get this, obviously. And then for this next pattern, we would now get
Anyway, it should go in like 10 minutes to
Okay.
learn some mathematics.
Mhm.
And so at any point, my headphones might be empty, be out
Okay.
of charge.
So we get this in the second step. Oh, you can see it.
Yeah, I think that's not what we want because that doesn't work for. Actually, it might work.
So now, but the next thing that we do is fill in these like empty corners, I think.
Yeah,
So we get this big cube.
I think. I think we shouldn't do that.
And then what we can do is we can sort of say, actually now we could say that we add sort of the edges here. I'm not sure, would this match? The problem is here, we need another pattern which is exactly the same pattern. But
Maybe we
here
should
sort of
first
have
fill the
two
corner
edges.
and then fill the edge.
And then we also need the permutation where we have 1, and here we have 2, and here we have 1, and here we have, well, and then it flips. Ah, we could mirror it. Okay, yes, then it would still work. Okay. What do you mean?
We could. Yeah, I think this is perfect. What I would do now is I would try to find all the nice patterns that generate the lattice and see what happens. And I think right now I already have 2 different ways. First, we could like start the generation from the middle, right? The thing you do now where you first in the middle get like a spike and then you fill up to the corners. Or you could start and extend the edge and then fill up the edge. You extend the corner and then fill up.
You mean this? You mean this?
Right. So, okay. No, not like this. Okay, so we start with this. And now what we could do is we could get to this.
Wait.
And then to
Okay.
this. Right? This is one idea where you first, in this step, you put something here, here, and here. And afterwards, you do this somehow. But another idea is you start.
Yeah, then you could say like there's a certain
Start
kind
like
of
this,
pattern. Yeah,
and
you
then
could say
you do
take
this.
the pattern of the corner.
So you could do this and then fill up this afterwards.
Yeah, I think there are lots of different ways to do it. I think these would all probably work. Maybe there's some which would work better, I'm not sure.
Yeah, and actually now we need to find out the root, because I think there's some chance that we actually need to incorporate more rules, more possible rules, not just
Yeah,
replace.
I'm pretty sure this works. I'm pretty sure there's like less
I'm pretty
than
sure
20
there
rules.
is a right version where this works. Yes.
Yeah.
But I'm not sure if our version or your version is right one.
So the interesting question is this actually sufficient to generate any graph?
Well, if you have infinite
think-
amount of, then yes.
No, well, I mean any compressible graph, any graph where the program, well, if we were to do use the Solomonov compressor, get the shortest program that generates the graph, it's not infinitely large. Like, is it possible to like all graphs for that with that property to be like described also with a finite sized pattern matching construction description?
Yeah, this is a very important result that you would need to prove to like
And I mean,
motivate it.
but it seems pretty likely to me that basically I would say it seems pretty likely to me that is the case. Maybe not for this, but there is
For
some
me,
version of the
it
pattern
would
matching.
seem like it is the case for some modification of what we did. I am not sure if the thing we did is exactly right. It could be that we need like
I
some
agree.
more options for the rules, not just a substitution, and maybe you need to like look at more things.
Maybe, not quite sure. Okay, because I want to go soon, maybe we could do a reflection now. How it
Yeah.
went. So, how did it
Thing
go?
was good.
Why? What was good?
We talked about actual things, and they were interesting. And we even have a potential theorem. And I think you can also look up, like under this like compressible graphs or something. Maybe someone already did work on that. Yeah.
Why was it good? Like, so I think like there was something that, so you said, for example, we did talk about actual things, by which you mean something more specific, right? You mean probably, okay, here's a phenomenon, I guess, that is sometimes happening. You talk to somebody and then they're like, yeah, here's this thing, it's so good, so it will work, and then, but then they talk about it sort of very vaguely, very abstractly, and you like can't even tell if it makes any sense, or like it's like.
I mean, I guess I liked it because we did some mathematical things.
Yeah, so you did some sort of like things that were where we know what we are talking about, because we're talking about graphs and we're like, look, we can maybe do this kind of thing in the graph. The graph is a well-defined thing. And we're talking about, I mean, we're doing it not really that formally, but I mean, you can do things too formally. And we talk about, yes, we have this function, we want to have this function, and this algorithm works like this, takes in the patterns, then matches them, then replaces things. Like that's a thing, a technical thing. I'm still confused what I mean with technical, but it's like this thing where you say things precisely. Like where the problem is not, I don't understand at all what you're even saying, I don't understand anything, because you just specify exactly what you're talking about in mathematics. Is that maybe something like that? That's what you thought was maybe good?
That's part of it. It's also that you can't easily just, like mathematics is like you get a hold in reality. But I think, yeah, maybe for our conversation, it was mostly that it's clear, yes, with which objects you are working.
Is that different from getting a hold in reality, or like what you mean with that? I'm not quite sure what you mean with that.
I mean that you can claim things and have intuitions, but maths can tell you no.
Ah, yes, you can. If you can state your thing in mathematics, you know, like somebody could say it's wrong what you're saying because you said these things like this. Now I can like use these logical deductive rules. Then tells me that doesn't make sense what you're saying. Like the algorithm that I was writing down, right? It's either like that's the thing that we want or it doesn't, right? Or like a something pretty close to that, right? Like I could be.
Or at least the algorithm is an actual algorithm, right? It's not like, okay, yeah, we add some edges and then it works.
Yeah.
Right? It's like an actual thing. And then for the reality, yes, you can then actually like prove if maybe. I mean, we didn't do that.
If we run the algorithm a bunch, then we would see, yes, that's, or like, then I would see, oh yes, look, this is, my intuition has been confirmed. It does something like that. Or I could be like, oh, it actually completely breaks always. I guess it wasn't right what I was thinking before. So it means that you can know when you're incorrect. Okay, talking about math was good because, and I think it was also that you actually were not so confused what I was talking about actually, right? I think in the past, when we were talking about stuff which I myself was still confused about and then only talked about conceptually, you didn't understand what I was saying because I was explaining it so well without being precise, I guess. And so
Yeah.
that maybe was making it a lot easier. Probably talking about concrete things in terms of graphs and other more formalized concepts probably helped a lot with conveying my ideas. It would be a usual occurrence before that I was trying to explain something to Matthias, but I failed because I was still confused about concepts myself and only tried to express them in vague conceptual language with minimal formalism, if any at all. But I'm not sure, I mean, I agree, writing things down in math or just being concrete in general, as you are when writing down algorithms, is a good thing for making you able to check whether the things that you are saying actually make sense. But well, was it actually... I mean, I think it's the same mechanism that makes it easier to understand things. I'm not sure that this specific thing was relevant for this conversation. Well, or maybe it... Well, I guess yes. It was about like... I tried to actually run the algorithm on the whiteboard instead of vaguely arguing about why this would work, which is like a good thing to do, I guess.
Maybe it was also because, like, when I was like saying something, like you didn't like completely, like you reacted and like actually, like I didn't felt like I was like you understood like my perspective, I think. Like when I said, for example, we should find like rules to generate the lattice graph, right? Like you just tried that then.
Yeah. Well, yes, because I thought it was a good thing to do.
Yeah.
I mean, if I thought it was a terrible thing to do, I wouldn't have done it. But maybe, I guess, so what you're saying is maybe something like, usually you might say things that make sense, but I don't understand them, and then I don't do them, or something like that. It might be possible. Okay, why did that happen? For some reason, Matthias felt more understood than usual by me.
I think it's because we're talking about some graphs.
Exactly. It might be like, it might be that usually when I fail to communicate things to Matthias, he would say things that just don't make sense from the perspective of my actual models, and therefore it would seem like I am dismissing everything Matthias says because it actually doesn't make sense for my models. But as I have failed to communicate them, Matthias doesn't generate suggestions based on my models, but based on some other thing that's not my models. That's probably a big part, I would guess. Because usually I'm like, yeah, but what you're saying is like bad. But I would guess it's bad because you can't, well, I mean, if you're like, I mean, if you play Counter-Strike, and then you think I'm playing Terraria, and then you say, yes, you need to get the shark gun that shoots really fast to kill the world eater. But then you say it in terms of the model of Counter-Strike, because somehow that was now mixed up. And then you say, yes, you need to buy the machine gun, and then you need to shoot the sniper. It doesn't make any sense. Right? Like something like that's probably happened. Something weird. Where like you have a model and you talk about and the model language is like the problem is something like Matthias has a model which is not accurate to my model, but the model that he has uses the same language as I have. It's like saying you need to get the shark gun to kill the world eater. because you think I'm playing Terraria, but I actually play Counter-Strike. But then they mix both the terminologies of the games, and so you actually say you need to get the machine gun to shoot a sniper, which doesn't make any sense, and it's a terrible idea. Okay, probably also that I was writing on a whiteboard was helpful. I don't think we didn't do that often in the past. Writing on the whiteboard was probably helpful for communicating ideas. I'm pretty sure that's really important. Anything else? What could we have do better?
No.
Well, okay, concrete improvements. Talk more about use formalisms to communicate ideas clearly. Use a whiteboard to communicate ideas clearly. I think basically, I would guess the main thing that we did better is that we were better at communicating. I think, well, okay, one thing I can ask, what could I do better in the math formalism? Maybe you can tell me. Or that's the thing you could watch out for, I think, sort of. Matthias could potentially watch out a bit more for when I'm doing a math formalism that's incorrect or could be done in a better way. Or I feel like that's what might provide a lot of value to me.
I mean, that's what I'm already doing whenever I see it.
Okay, but did you do it once today?
No.
So it means I must have done the perfect math formalism. According to you.
I mean, we didn't like write down the things. We just
we didn't do
talked
completely
about
formal.
things, and like the being grounded in graphs was, and like about the particular objective was enough for me to get all the things.
Okay, nice. Well, then just as a note, keep doing that. Or keep saying, oh, maybe we need to be more formal here. But, well, actually I think you said it a bit too often in the past, at points when it was actually not useful. But I think there might be probably situations where I am not formal enough where it would be better to be more formal. Like I think probably that we did this, well, on the object level, using the subtype thing was probably just distracting, could just have done it in a different way.
Yeah, I mean, that was just like a tangent, but I think that's okay.
Yeah.
I don't think it was like central to the thing we are talking about, but I think it was still okay to talk about.
Yeah, but that's a good point. It's like we did get sidetracked by talking about subtypes and what they are. Though a good thing about that was that we managed to get back on track relatively quickly within less than 10 minutes, I think. Definitely less than within 15 minutes. Which I think didn't even take ADHD medication today and still managed to notice that and get back on track, which seems pretty good. Okay. Yeah, maybe this is also important. I don't know. Maybe I'm more annoying if I take ADHD medication. I didn't take methylphenidate. Maybe this makes me less annoying, but I'm not sure. Okay, anything else? Oh, maybe next steps. So where we left just off right now would be like figure out what are some set of simple graph substitution rules that would generate a 2D lattice and more generally any n-dimensional lattice graph. And then there is like, what is the general structure detection algorithm that can be used to infer what the graph generating function is? Yeah, these are the most important next steps, I would think. And I guess then there was also a thing like continue the comparative analysis of Solomonov induction and graph matching substitution, like world models and inference procedures. Okay. Anything else?
No.
Okay, then if you meet any people, okay, now I guess I can sign off from this.